All right. So it's been a while. Might take a little bit to get back in the swing of things. I do have a quick announcement. That next week, on the Wednesday, we will not have class. I mean, March 30th. I'm going to be away at a conference in the University of Georgia during that time, and I'm still able to cover everything that I need to. So I figured let's just have a day off. Okay. And, for some reason, I had 2 class periods budgeted for this next topic, but given the amount of notes that I have, it really should be possible in one. So that was one reason for not having class the Wednesday before break. So we'll see how it goes. This recently I've done a review from material covered in Math 560, 460, 560, on how to solve nonlinear equations, how to find roots, using various methods. And now we want to use techniques like those to solve systems of nonlinear equations, as opposed to a multivariable case. Okay. So here's the problem that we're going to solve. So we have a function capital F that has n inputs, n outputs, so that's Rn to Rn, and it has these component functions, n of them, each one a function of n variables that return to scalar. So capital F of x is a vector quantity, and we want to find a point in Rn, x star, such that capital F of x star is equal to 0. So we will find a solution to a system of n nonlinear equations in n unknowns. So a logical choice for a method to generalize from the single variable to multivariable case is fixed point iteration, because it's such a simple method to describe. Because what is fixed point iteration? It's nothing more than choosing the initial guess and then repeatedly substituting it into your function g. So we can just do that in the multivariable sense too. So you choose the initial guess, which would be a vector in Rn, and then we keep substituting it into g, where we've rewritten the equation f of x equals 0 as the form x equals g of x in some way. And then hopefully this iteration will converge. And since we have substantial theory on convergence in the single variable case, we certainly need to generalize that to the multivariable case. So one example of how you can rewrite f of x equals 0 as x equals g of x is kind of like what we had in the single variable case. The g of x equal x minus something times f. Now, before, in the single variable case, we had like x minus lambda f of x, where lambda had to be some non-zero constant. Here, it's sufficient, it works for multiplying f of x by a matrix A. So this is a matrix vector product, where the matrix A is just required to be invertible. So suppose g of x equals x, then we would want a times f of x to be the 0 vector. And if A is an invertible matrix, the only way a times f can be 0 is if f of x is 0. So g of x equals x implies f of x equals 0. And then similarly, if f of x equals 0, then certainly g of x will equal x. So you confirm that g of x equals x if and only if f of x equals 0, as long as A is invertible or non-singular. And I tend to go back and forth and use these terms interchangeably, so I want to make sure that everyone here is aware of them. Invertible versus non-singular. So what about convergence? What can we say about that in the multivariable case? So a quick recap from the single variable case. If your function g maps an interval a, b into itself, right, gives you existence of a solution. And then if, assuming g is differentiable, if the absolute value of the derivative is bounded by some constant less than 1 on that interval, then the solution is unique and fixed point iteration is guaranteed to converge. So what do we want in the multivariable case? Similarly, the function capital G needs to map some domain D and Rn into itself. And if I define this matrix, J sub G, to be the Jacobian matrix of G, in other words, it consists of all the first partial derivatives of the component functions of G with respect to all of the independent variables. So for working in Rn, we have an n by n matrix. So this is playing the role of G prime from the single variable case. And what do we want to be true of this matrix? The sufficient condition for convergence is that some norm of a Jacobian, recall I talked about norms with respect to iterative methods and also the condition number, that should be bounded by some constant rho that's less than 1. Now, this is a natural choice of convergence criterion because we actually have seen fixed point iteration before. It just didn't really describe it that way. For iterative methods, we talk about stationary iterative methods such as Jacobi, Gauss-Seidel, and SOR. They all have this form. And this can be written as fixed point iteration. Xk plus 1 is g of xk, where this is I've written it this way for convenience. So this is a function g that you're dealing with in this case. Now, here we're solving a linear equation, so the function g is linear. So the Jacobian of g is just whatever is multiplying x, which is m inverse n. So when we dealt with stationary iterative methods, what I told you back then was that the norm of m inverse n being less than 1 is sufficient for convergence. And then this stronger condition, rho of m inverse n, is necessary and sufficient for convergence. So we'd like to have the same kind of thing with a system of nonlinear equations, ideally the spectral radius of the Jacobian matrix being less than 1 as a necessary sufficient condition. But it might be easier to establish this if the norm is less than 1. So here's an example. I have a system of 2 nonlinear equations and 2 unknowns. So we're working in the xy plane, or the x1, x2 plane. Now, if you want, you can think of x1 as x and x2 as y, just for convenience. So I need these 2 equations satisfied simultaneously. So this equation, if I focus on the solution to this, we'll have infinitely many solutions that describe a curve in the plane. So what kind of curve would this be? Yeah, it's parabola, like y equals x squared. And what about this one?
I'm drawing it, whatever you call it. Inverse, sort of the parabola.
Oh.
Circle.
Yes.
Oh, I'm sorry. I guess I'm looking below it.
Oh. Okay. Yeah, this is a unit circle.
Mm-hmm.
All right, so we want the unit circle to cross this parabola, and if you were to draw that, then you would see that there are 2 points where they intersect. So we focus on just trying to find one of them that lies in the first quadrant, where x1 and x2 are both positive. I'd like to write this in the form of a fixed point iteration. So x equals g of x. So I take the first equation, actually I didn't take the second equation and solve it for x1. then I take the first equation, which is already in the form x2 equals something. So here's one way to write this system of equations in the form x equals g of x. So this is my function g in this case. So, actually, see if I can try this. Okay, so I'll find g, view this function. Okay, so square root of, actually, two arguments. Well, I'll make the argument a vector for convenience. So the output will have to be a vector. So I'll deal with x of 1 and x of 2 with two elements. So the first element is square root of 1 minus x2 squared. And the second element is just x1 squared. Okay. Now, so I can assume that I work against domain x1, x2 between 0 and 1. Now, if x1 and x2 are within 0 or 1, then g of x1, x2 will also be between 0 and 1. So g does map this domain into itself. So let's see what happens. If I just pick the midpoint of this box, so x1 and x2 both equal 1/2. Half, 1/2. Okay, so now we'll do x equals g of x, and we'll see what happens. All right. If you look at each individual component, kind of bouncing around. Okay, actually, hang on. What I'm going to do, I'm going to set it back to this. I want to show this. Okay, so x equals g of x. And I'll plot x1, x2 with a circle. Okay. I'll do a hold on. Oh, might have a graphics window already open, so I'll just run it again. Okay, so here we are, and now I'm going to keep running this. Oh wait, I'll close the editor. Okay, I want to put the figure up each time. I don't know if you can see these dots. I'll just run several iterations. But they're literally all over the place. And they seem to be gravitating towards the boundary. In fact, here we have iters going towards this corner, iters going towards this corner, towards this corner. If I keep going, I'll just do several more iterations. They're heading towards the corners, which is definitely not a solution. So this choice of G is a bad one. That's not producing convergence. So we'd like to get some idea as to why this is happening. If we look at the Jacobian of G, then this is what we get. And so what would happen is, as I suppose x1 is greater than 1/2, then right away that would mean that the 1 norm or infinity norm of Jacobian would be greater than 1. So it's possible to find points where that happens. That is In a single variable case, having a derivative greater than 1 would lead to divergence, even if x is really close to the fixed point. So let's reconsider our choice of g, where I take the first equation for the original system and solve it for x1, and then take the and then here I'm rearranging this equation to solve for x2. So here I'm using the inverse function, which is recommended in the single variable case to fix a bad choice of g. So here's our Jacobian this time. Now, it is still possible to find choices of x1 and x2 that make this large, but it turns out, but if I just go ahead and try this iteration, and we'll see what happens. Okay. So now I'll have x1 as the square root of x2. Okay. And x2 is the square root of 1 minus x of 1 squared. Okay. All right, there's our initial guess. So now I'll do this again, and let's see what happens. Okay. There's still some jumping around. But what appears to be happening this time?
Going towards the center.
Yeah, they're converging towards something. They're still dancing around the circle, but now they're converging on a point instead of diverging to the corners. So I'll run several iterations more. Yeah, there's definite convergence. Okay. So now that I appear to be converging, if I take a look at the x that we get, and then I want the Jacobian matrix here, so it's a 0, and then 1 over 2 square root of x2. And then minus x1 over square root of 1 minus x2 squared. And then 0. So for these choices of this particular x, this is our Jacobian. And if I look at the eigenvalues of a Jacobian, they're both less than 1 in absolute value. So that would explain why there's convergence, but slow convergence. Because it's not much less than 1. All right. So it's almost as difficult to establish conclusive theory in the multivariable case. Like for example, the existence of a fixed point in a single variable case, that G maps an interval AB into itself, it's very easy to prove that that guarantees the existence of a fixed point, because you can use Brouwer's theorem, which rests on the intermediate value theorem. But the intermediate value theorem does not have a direct analog in higher dimensions. So proving the conditions for the existence of a fixed point in higher dimensions is more difficult. But some of the same concepts apply. Like in a single variable case, we want G prime to be smaller than 1 absolute value. Here we want the spectral radius of a Jacobian to be less than 1 near a fixed point to help with convergence. But you still need a decent initial guess. Okay. All right, so are there questions about fixed point in higher dimensions? Notice in this case, when it's formed a matrix, you can see that one of the elements was greater than 1 in absolute value. So the norm of a Jacobian would be greater than 1. But the norm being less than 1 is a sufficient but not necessary condition for convergence. So having a norm greater than 1, it might be indicative of a problem, but it's certainly not a deal breaker. So that's with iterative methods for x equals b. The spectral radius is where it's at when you're trying to be sure about convergence. All right, so that's one method that was generalized from one variable to several. But we can also generalize Newton's method. Now, here is the same Newton's method that I covered earlier, just written a little differently. So the way I've written it before is xk plus 1 is equal to xk minus f of xk divided by f prime of xk. But I can just write it as multiplying by 1 over that. And I've written it this way so you can more readily see how it generalizes to a higher dimension. So instead of thinking of it as dividing by the derivative, I'm multiplying by the inverse of the derivative. And that's what is happening in the multivariable case. So I'm trying to solve capital F of x equals 0. So xk plus 1 is equal to xk times the inverse of a Jacobian matrix. So here I'm multiplying by the inverse of the appropriate derivative, which in this case is a matrix. So I can't really think about dividing it anyway. I have to multiply by the inverse. And hopefully the Jacobian is non-singular or I'm going to have trouble. So what we have here is a inverse of a matrix times a vector. But another way to think about it is, if I refer to this entire term, including the minus sign, as a vector sk, sk is a solution of this system of equations. So here I have an ax equals b problem. So minus f of xk, that is my b. The matrix, the Jacobian matrix, is my A, and the SK is my solution. So I can just solve that system by whatever means I can. Using Gauss elimination of partial pivoting, for instance, or maybe even using an iterative method. So an iteration within an iteration. It just depends on the kind of matrix you're dealing with. But what we can see is that we have a lot more work on our hands, because now for solving a system of n linear, nonlinear equations and n unknowns, we had to perform order n cubed operations every Newton iteration to solve this system. The kind of convergence that we know about from the single variable case holds true in the multivariable case, that generally you have quadratic convergence. But if the, like we saw before from Newton's method, if the root x star was a double root, meaning its derivative was 0 at the root, then convergence would be linear. It would slow down to linear. Similarly, if Jacobian at the root is singular or not invertible, then we could have this iteration breaking down, or at least convergence would slow. So this is the same kind of pitfall. We're just describing a situation in linear algebra terms this time. There's questions about what happens with Newton's method. Okay. Now, as I mentioned, we already know from single variable case, Newton's method, okay, it's not reliable. Also, each iteration is expensive because you have to evaluate f and a derivative. But as I just mentioned a little while ago, when you're solving systems, the problem is even worse. You have a lot of expense involved in solving this system of equations to get your step that takes you from xk to xk plus 1. So, so now Newton's is really impractical because of this derivative evaluation and computing this. So in fact, solving the system's the worst part. You do it to evaluate n squared partial derivatives. That's bad enough. But then you're doing even more work here. Now, there is always a possibility of the secant method. Because the secant method, you're replacing the derivative computation by a difference quotient involving the previous two iterates. You can try that here also. Instead of evaluating the exact partial derivatives, like in other words, using formulas for derivatives of your original function f, you could do the same kind of difference quotients where you're taking the derivative of each component function of f with respect to, so you're approximating each partial derivative of a component function with respect to appropriate variables by taking a difference quotient involving a component function of f in the numerator, and in the denominator you'd have the difference of two individual components of xk and xk minus 1. And that might help you here in reducing that expense. Like you don't need the actual partial derivative functions of f. But you still have to solve this system. So simply changing Newton's method to the secant method, like we do in a single variable case, it helps a great deal there. But here it doesn't really help you that much. The main source of inefficiency is still there, it's still just as bad as before. So that's why just plain old secant method, it's like, we need to think of something else to reduce this substantial expense of solving these systems. And that leads to what is called Bruids method. So this is a uniquely multivariable method. So the idea is we use an approximate Jacobian that can be updated during each iteration. So how do we obtain this approximate Jacobian? It's kind of strange. I'll just warn you about that up front. First iteration, go ahead and compute a true Jacobian. Right, so you are going to incur that one expense the first time, but then hopefully reduce it in subsequent iterations. Okay. So how do you define each new Jacobian in terms of the previous ones? So our approximate Jacobians are A0, A1, A2, A3, and so on. First, you have what's called the secant condition. That's for your approximate Jacobian AK times the difference in x's is equal to the difference of the corresponding y values, or f values. Now, why does this make sense? If this were in a single variable, we could say AK is equal to change in y divided by change in x, in other words, a derivative. So now we can't do the same thing in a multivariable case. We can't divide vectors, but we can say a matrix times a vector equals another vector. So what we're saying is, at least along this direction, which is really the only direction we care about, going from one iteration to the next, that AK will be a good approximation of a true Jacobian along this direction. Then, if we're considering any direction z that's orthogonal to this direction, we just preserve the value of the previous approximate Jacobian. So AK times z is equal to AK minus 1z. And this covers most of the space, because if we're in an n-dimensional space, there are n minus 1 directions orthogonal to this one. So for all those directions, so most of the space, the Jacobian just behaves like the previous one. Now, it turns out it is possible to construct a matrix AK that satisfies both of these conditions. That for a specific direction, or for a specific vector, the matrix product is equal to this given vector here, and then for all directions orthogonal to it, it's equal to some other known matrix. And here's the formula. So AK is equal to AK minus 1 plus this rather strange expression. Now, the vector UK that I've written here is defined to be this entire fraction. Now, what is this fraction? Well, the numerator is a column vector. The denominator is just a number. So this whole fraction, the UK, that's a column vector. A column vector times this, which is a row vector, that's called an outer product. As I mentioned down here. So U, V transpose, where U is a column vector, V is also a column vector, so V transpose is a row vector. That's an outer product, which is a matrix. As opposed to U transpose V is an inner product or dot product, which is a number. But what's interesting is an outer product times a vector is equal to this vector times an inner product. So matrix vector multiplication involving an outer product is actually very easy to perform. It only requires order n operations instead of n squared. So this outer product, a key feature of an outer product is that it has rank 1. And so this is something that actually can be proven. Actually, I think I gave us a homework problem in Math 610. I think I did anyway. I'll actually remember. Okay, so AK is equal to the previous A plus a rank 1 update. That's what this is called. So anytime you're adding on a matrix of rank 1, it's a rank 1 update. So anytime you have a matrix that is a rank 1 update of another matrix, you can use what's called a Sherman-Morrison formula to express the inverse of the update in terms of the inverse of the original. So since AK is related to AK minus 1 by this rank 1 update, the inverse of AK is equal to the inverse of AK minus 1 plus a different rank 1 update. So that's what the Sherman-Morrison formula says. That if B is a rank 1 update of A, B inverse is a rank 1 update of A inverse. And the formula tells you what that rank 1 update is. So we can actually explicitly represent the inverse, and very efficiently, because carrying out all this work and also multiplying this matrix by a vector, because we're going to multiply, because we still need to compute this, where instead of a true Jacobian here, we're going to have the approximate Jacobian. This would be a matrix vector product. So we're actually going to be multiplying this by f of xk, but that takes only order n squared work. So we're never performing Gaussian elimination, which is order n cubed. So we've reduced the work per iteration by an order of magnitude by using the Sherman-Morrison formula to get our approximate Jacobian instead of, and then solving the system that we need to solve, where it's just matrix vector multiplication by an inverse, instead of solving this system at every iteration using Gaussian elimination or whatever other method that would cost order n cubed operations. There are questions about how this works. Now this is the essential ingredient in Bruids method, but what I'd like to do for completeness is show you the actual Bruids method. Because these other methods that we see, Newton, secant, fixed point, those are all very short algorithms. So it's enough to show you what the main step is. But that's not so a Bruids method, it's a more complicated algorithm. Okay, here it is. All right, so we have our initial guess. First iteration, we go ahead and compute the true Jacobian. So this part is the first iteration is exactly the same as the Newton's method. Everything we do here inside the for loop deals with the actual Bruids method where we work with approximate Jacobian. Really, and notice wherever you see AK or AK minus 1, it's only the inverse. We never actually explicitly compute AK. We don't need to. So this right here is the main step in getting the approximate Jacobian. This is where we use the Sherman-Morrison formula. And these other variables are only needed to make that process more efficient, just by saving certain sub-expressions that appear more than once. And then we take that inverse and multiply it by f of x, or minus f of xk. So this is similar to the main step in Newton's method. Actually, this part is exactly like Newton's method, these two lines right here that I've highlighted, except in Newton's method, this would be the true Jacobian. And you carry this out by performing Gauss elimination forward back substitution. Whereas in Bruids method, this is carried out by a matrix vector product of an inverse that's obtained explicitly. And this is exactly the same as in Newton's method. We're just updating with SK. So during this iteration, we compute our new approximate Jacobian. That's what these highlighted lines do. Use it to get the step from xk to xk plus 1. Go ahead and take that step, and then we keep going. There's one more thing I want to spend a little time on, but first I want to see if anyone has any questions, whether it's about this or homework problems. Okay. I'll take a little time to show you how we get the Sherman-Morrison formula and why it works. I found it to be a fun exercise, if ugly. Okay, now I have it written out here. So here's our situation. Let's suppose that for a matrix A, let's suppose A inverse is known. And we also know that B is a rank 1 update of A. So B is equal to A plus this outer product of some given vectors U and B. So how can we get B inverse in terms of A inverse in this situation? So first, if I look at, suppose I define the vector x, so that AX is equal to U. And A is invertible, so X is just A inverse U. So now if I compute Bx, then Bx would be equal to this times X, just by the definition of B. But then A times X is equal to U. And here we have U times V transpose X. But V transpose X is a dot product. It's a scalar, a number. So I can move it around wherever I want. And that's what I've done here. I have, so this is equal to A times X, which is U, and then U V transpose X, but that's the same as V transpose X times U. So I can write it like this. So now I can multiply both sides of this by, actually, okay. I can multiply both sides of this by B inverse and rearrange, and now I have this expression for B inverse U in terms of A inverse U. It's just multiplied by this scalar. So now I know what B inverse U is supposed to be. I want B inverse U in general. Here I only know how it behaves along one direction, but that's my starting point. Next, suppose I deal with a vector x such that V transpose A inverse x is equal to 0. Then, what I can do is, so now I have the following. B times A inverse x, which is a vector, and now I replace B by its definition, but now A and A inverse cancel out, so now I just have x from the first term. And here I have U V transpose A inverse x, but V transpose A inverse x is assumed to be 0, so I'm left with only x. So now I can rearrange this equation, and I get B inverse x is A inverse x. Now, to recap, for this one direction, U, I know what B inverse does. I know what it produces. Now, for x that satisfies this, which is an n-1 dimensional space, it's a set of all vectors that are orthogonal to this vector, or its transpose really. I know that B inverse and A inverse behave the same. So I have this condition that applies to an n-1 dimensional space. I have this condition that applies to a one-dimensional space. In other words, I've covered n dimensions, the whole space. That means that these two equations are enough to define B inverse completely. But how do I get the actual formula? That's the question. So to do that, I'm going to define the problem more abstractly, just also to simplify the notation. So think of it this way. I'm given this matrix C, and I'm going to find a matrix D that satisfies these conditions. D times some specific given vector W equals some other given vector C. So that corresponds to this condition right here. Just with simpler notation. And D is equal to C when applied to any vector Y that's orthogonal to a given vector G. So again, this condition applies to one dimension, this condition applies to an n-1 dimensional space, together that covers the whole space. Now, this is an abstraction of a problem of finding B inverse, where here's the corresponding between them. C is A inverse, D is B inverse, W is equal to a vector U that defines B, Z is equal to this mess, which is why I changed the notation. And then the vector G is equal to this vector that is orthogonal to X. It turns out that the solution, the matrix D that satisfies both of these conditions, is this vector right here. Oh, sorry, this matrix right here. And this is a homework problem to prove that. I don't think I assigned that problem. I'm going to check. Oh, I didn't assign any homework from this section. Okay. So I can do this problem. Suppose I multiply both sides of this by W, vector W on the right. So dW on the right, then I have CW here. I have G transpose W, which is a number, that cancels with a G transpose W down here. So all of that cancels. So now I have CW plus Z minus CW. CW is canceled, and I'm left with Z. So this condition is satisfied. On the other hand, if Y is orthogonal to G, I multiply both sides of this by Y. G transpose Y is 0. So this whole term goes away. So dy is equal to cy in that case. So if I take this formula for D and make all of these substitutions, which is what I've done here, then I have a formula for B inverse. Now this is an extremely ugly one, but it can be simplified, resulting in this. This is a Sherman-Morrison formula. So that's a general idea of how it is obtained. It's just really, really messy algebra. You gotta be really careful. Keep in mind that a lot of things, times you're dealing with matrices, vectors, things like that, and what operations you're allowed to perform there. I should mention, there's a generalization of a Sherman-Morrison formula called the Sherman-Morrison-Woodbury formula that applies to a rank K update. So instead of a situation like this where U and V are vectors, and as matrices with one column, if U is a matrix with K columns, and V is also a matrix with K columns, then this is a rank K update, and there is a generalization of a Sherman-Morrison formula to the rank K case, and that's Sherman-Morrison-Woodbury. So I was not wondering, like, did Woodbury come up with it all by themselves? Or did they work with Sherman-Morrison? Or I have no idea. I should have looked this up, I just haven't. And it's always fun to examine the history of these things when I get the chance. Okay, so this is how we are able to efficiently obtain an approximate Jacobian just by ensuring that the secant condition is satisfied and that on the rest of the space, the new approximate Jacobian mimics the action of the previous approximate Jacobian. But that would work a whole lot better if you have a decent initial guess. Because the idea is, you're evaluating a Jacobian at xk, and the xk's are converging to x star. So, as convergence is happening, is a Jacobian really changing that much anyway? It shouldn't be. Now, if you have a faraway initial guess, then yes, it is going to change a lot. So Bruids method, like Newton's, ought to have a decent initial guess. I don't recall if I commented on the convergence of Bruids. Not likely to be quadratic. Oh, you know what? I don't talk about it here. I don't think. I don't know off the top of my head, but my hunch is it would be superlinear convergence, like the secant method, which also relies on an approximate derivative. That's really what we have going on here. I'll look it up. Okay, so that'll do it for systems. So let's see what's coming up next time. We're getting into ODEs. In fact, it's all ODEs the rest of the way. Initial value problems first, chapter 12, and then chapter 13 is a little time on boundary value problems, which is the subject of the coding option for the final. So hope you like ODEs.